Here we are now on one of my software-defined data center deployments based off the VMware Validated Designs, specifically the Single Region IT Automation Cloud VVD. Here we'll take a look at some of the architectural constructs as well as the key products and capabilities used in this VVD. For example, the vSphere platform, VRealize Log Insight, VRealize Operations, and VRealize Automation. Let's get started by logging into the vSphere web client. Here in the vSphere web client, we can manage the entire platform for the software-defined data center, the well-known compute virtualization, along with software-defined storage and software-defined networking. Recall that the basis of the platform is vSphere 6.0, and that we are using some of the key platform enhancements and capabilities of this release. For example, Enhanced Link Mode allows us to interconnect both the management and compute stacks for visibility under a common single sign-on domain. Let's take a look at the Administration and System Configuration section of the web client. Here we can see that there are 4 nodes and 52 services running. We can also see the overall node health and service health for these infrastructure services. If we drill down, we see that there are 2 infrastructure nodes that provide platform services for the management and compute stacks, and 2 management nodes that provide vCenter server instances for the same stacks. This linkage will allow us to see the infrastructure as a whole. VMware Validated Designs are built on a collection of physical data center racks that are interconnected using a common network core. Inside the physical racks, the different functions of the software-defined data center are implemented as a standardized set of building blocks, referred to as pods. Each pod encompasses a combination of servers, storage, and networks that are required to fulfill specific roles within the software-defined data center. These designs dictate 4 types of pods: management, edge, compute, and storage. Let's take a look at 3 of these essential pods and explain the role of each pod. We'll start with the management pod. As the name implies, the management pod hosts the infrastructure components used to instantiate, manage, and monitor the software-defined data center. The management pod is deployed inside a single data center rack and is comprised of a minimum of 4 physical servers and 2 redundant top-of-rack switches, commonly referred to as leaf switches. The physical servers used in the management pod must be virtual SAN ready nodes, meaning they have been certified for use in a virtual SAN deployment. Storage for the management pod is provided using a combination of VMware Virtual SAN and NFS. Virtual SAN is used for hosting the virtual machines that run the management cluster, where NFS is used for storing backups, log archives, virtual machine templates, and ISO images. VMware ESXi is installed on each of the 4 physical servers, which are then logically grouped into a vSphere management cluster. Notice that the advanced resource management settings for the vSphere Distributed Resource Scheduler and vSphere High Availability are enabled. As is Virtual SAN. Let's look at the configuration of Virtual SAN. Here we can see that Virtual SAN has been enabled across the 4 nodes in the management cluster, combining flash and magnetic disk for the caching and capacity storage tiers. Here we can also manage and create additional Virtual SAN disk groups across the cluster for added cache and capacity. Within a given VVD, there will be 1 management pod. To accommodate future growth and scalability, additional Virtual SAN ready nodes can be added to the management cluster in order to provide additional compute, network, and storage capacity. Now let's take a look at the Edge pod. This pod provides a centralized gateway through which workloads running in the software-defined data center are able to access external networks. By design, business and end-user workloads running in the SDDC are isolated on their own Layer 2 private network and do not have direct access to external networks. To access external networks, traffic must be routed through the Edge pod using a shared NSX transport zone. Like the management pod, the Edge pod contains a minimum of 4 vSAN ready nodes. Due to its relatively small size, in terms of hosts, the Edge pod is typically co-located inside the same physical rack as the management pod. Note, at the time of this recording, I only had 3 nodes in my Edge pod. Sorry about that. Here again, VMware ESXi is installed on each physical server, and the servers are logically grouped into a vSphere edge cluster. The edge cluster is managed from the Compute vCenter server instance running in the management pod. Storage for the edge pod is provided by VMware Virtual SAN. Within the VVD, there will only be one edge pod. Now let's move on to the compute pods. Within the software-defined data center, all business and end-user workloads run inside the compute pods. Like the management and edge pods, the compute pods are deployed inside data center racks, with each rack representing a separate pod. Each compute pod contains a minimum of 4 servers, along with a pair of top-of-rack leaf switches. As with other pods, VMware ESXi is installed on each server, and the hosts are logically grouped into vSphere clusters. Compute clusters are managed by the Compute vCenter server instance running in the management pod. Storage for the compute pods can be any combination of supported vSphere storage. The type of storage used is determined based on cost, performance, business requirements, and desired service levels. As you can see here, VMware Virtual SAN has been enabled in this compute pod. In addition, the pod design makes it possible to deploy separate compute pods with varying levels of quality, redundancy, and availability in order to support different types of service levels required by the software-defined data center. Let's take a look at the virtual machines running across the stacks that instantiate and manage the software-defined data center. Here we've organized the components into their own folders. In the management cluster, there are 2 separate vCenter servers deployed along with 2 corresponding platform service controllers. The 2 platform services controllers are configured as replication pair for a single sign-on domain. One vCenter server instance, which is referred to as the management vCenter, is used to instantiate and manage the management cluster itself. The second vCenter server instance, which is referred to as the compute vCenter, is used to instantiate and manage the vSphere clusters running in the edge and compute pods. VMware NSX is also installed on the management cluster to provide network and security services such as VXLAN, virtual switching, firewalling, and load balancing. Here you can see the NSX Manager and NSX Controller cluster for the management pod. For security purposes, that is, the separation of NSX management and control planes, the NSX Manager instance for the edge cluster is deployed in the management cluster, while the NSX Controller cluster runs inside the edge cluster. Next up is VRealize Operations. The VMware Validated Design uses VRealize Operations to provide monitoring and alerting services for the software-defined data center. VRealize Operations is deployed in 2 parts, the analytics cluster and the remote collectors. Both components are deployed in the management cluster. A 4-node VRealize Operations analytics cluster is deployed inside an application virtual network. The analytics cluster consists of 1 master node, 1 master replica node, and 2 data nodes. The use of multiple nodes allows for both scalability and high availability. In addition to the analytics cluster, 2 remote collector nodes are also deployed in the management cluster. Remote collectors help to lighten the load on the analytics cluster by collecting metrics from applications and then forwarding them in bulk. Now on to VRealize Log Insight. VRealize Log Insight provides scalable log aggregation and indexing for the software-defined data center, with near real-time search and analytics capabilities. As with VRealize Operations, VRealize Log Insight is also deployed in a highly available and scalable manner comprised of a minimum of 3 nodes, a single master node, and 2 worker nodes. And now VRealize Automation plus VRealize Orchestrator. VRealize Automation enables modeling of complex IT services inside reusable blueprints. These blueprints are published within a centralized service catalog and made available for automated provisioning. Along with automated provisioning of IT services, VRealize Automation also provides a self-service portal that empowers IT to take full advantage of the rapid provisioning capabilities of the software-defined data center through automated deployment of new workloads as well as enabling virtual machine lifecycle management. VRealize Orchestrator works hand-in-hand with VRealize Automation through the use of both out-of-the-box and custom workflows to extend the automation capabilities, and allows for a fully automated deployment of complete multi-tier application stacks in minutes. Both VRealize Automation and VRealize Orchestrator are deployed in a highly available and scalable manner inside an application virtual network, with multiple nodes based on service roles across the stack. Now vSphere Data Protection. vSphere Data Protection is deployed on the management cluster and used to provide data protection for the virtual machines residing in the management cluster. Once deployed, the vSphere Data Protection Appliance is registered with the Management vCenter server instance. Within vSphere Data Protection, backup policies are created for various applications running in the management cluster. And lastly, we have templates. Virtual machine templates are used by VRealize Automation and are synchronized across pods by the content library, and then stored on NFS in a format that's consumable by VRealize Automation. Here we can see some of the example templates for CentOS, Ubuntu, and Windows Server. Now let's take a quick look at the storage provided to these pods. We've sorted the types of storage for the management and compute stacks in their own folders. Recall that we use Virtual SAN for the management and edge pod workloads. We also use NFS in the management pod for backups, log archives, and templates. You can also use any HCL supported storage for compute pod. This SDDC is using Virtual SAN for the storage consumed within the compute pod. The foundation for the software-defined networking provided by NSX is based off the vSphere distributed switch. A vSphere distributed switch is created for each pod. Here we see the management vSphere distributed switch created within the management vCenter. It includes the necessary VM kernel port groups for management, vMotion, Virtual SAN, and NFS. Additional port groups are provided for public access to application virtual networks and the NSX VXLAN tunnel endpoints. Jumbo frames is enabled on the distributed switch port groups for both Virtual SAN, NFS, and NSX. Each host has two 10 gig uplink connections to the top-of-rack leaf switches. Similar vSphere distributed switches are also created in the Compute vCenter for both the Edge and Compute pods. Here we can see that the vSphere distributed switch has been applied into its corresponding pod. Let's dive in and look at the NSX configuration and how it provides network and security services such as VXLAN, virtual switching, firewalling, and load balancing to the software-defined data center. Recall that the NSX managers have been deployed to the management pod. One was registered with the management vCenter and the other with the compute vCenter. The NSX controller cluster for the management stack is deployed in the management pod. The NSX controller cluster for the compute stack is deployed in the edge pod. The hosts in the management pod have been prepared for NSX. As have those hosts in the edge and compute pod. In the logical network preparation, we can see that the VXLAN tunnel endpoints have been established on the host in the management pod. Here, the VXLAN network identifiers have been set. And a management transport zone has been created to delineate the scope of the VXLAN across all nodes in the management pod. Here in the NSX manager for the compute stack, we can see that the VXLAN tunnel endpoints are prepared on the host in the edge and compute pod. A VXLAN network identifier pool has also been set. And a compute transport zone has been created to delineate the scope of the VXLAN across all nodes in both the edge and compute pod. Recall that the compute pods share the same NSX instance as the edge. Compute pods do not have direct access to external networks. To access external networks, the workloads running in the compute pods route traffic through the edge pod using a shared NSX transport zone. A key design element of the VVD is the concept of an application virtual network. The VVD takes full advantage of VMware's compute, storage, and network virtualization capabilities in order to fully maximize the benefits of the SDDC. This includes leveraging the NSX logical switch and the NSX Edge Services Gateway to isolate and secure both management and tenant workloads running within the software-defined data center behind an application virtual network. An application virtual network is a construct where applications running in the software-defined data center are placed on an NSX logical switch. The logical switch implements an isolated Layer 2 network. This isolated network is then fronted by an NSX Edge Services Gateway, which provides routing to external public networks and, if required, vSphere management networks, together with firewalling, load balancing, and NAT services for the application. Application virtual networks also facilitate application portability between sites and thereby allowing virtual machines to be easily moved between data centers in response to disaster recovery events without the need to change IP addresses. Here we can see application virtual networks created for both VRealize Operations, VRealize Log Insight, and VRealize Automation solutions. Before deploying VRealize Operations, Log Insight, and Automation, the VVD establishes an application virtual network for each solution. The application virtual network consists of a dedicated logical switch with its own IP space, together with a highly available pair of NSX Edge Services gateways. Solution component nodes are then deployed and assigned an IP address within this IP space. Following the deployment, a virtual IP address may be reserved and assigned for when load balancing is configured on the Edge Services Gateway, along with any necessary NAT and firewall rules. Here we can see all the NSX Edge Services gateways in the management pod, which are connected to the application virtual networks for VRealize Operations, Log Insight, and Automation. Let's take a look at the one for VRealize Automation. High availability, load balancing, and routing are all up and applied. Here we can see the interfaces of the Application Virtual Networks Gateway. These include the public interface, management infrastructure interface, and the internal L2 network interface. Source and destination network address translation rules have been created. Any necessary static routing has been added. And of course, load balancing is operational for the VRealize Automation components. Application pools, service monitoring, pools, and virtual servers have all been configured to scale and protect the cloud management portal infrastructure. And there you have it, a quick tour of some of the key architectural concepts and solutions used within the VMware Validated Designs. For more information, visit vmware.com/go/VVD.